Right now, a health system just spent years and millions of dollars building a genuinely impressive AI agent. And most hospitals still can't get anything like it running on their own floors. That's not a hardware problem. That's not even really an algorithm problem. Here's the mind-blowing realization. There's a massive valley of death between a brilliant model sitting in a sandbox and a functional AI co-pilot actually running inside a hospital's live systems. Almost none of the AI research you hear about ever crosses it. In this explainer, we're going to look at the exact blueprint one hospital used to actually cross it.
Why are these AI doctors stuck in the lab? Well, our healthcare systems are completely overwhelmed. Clinicians are literally drowning in unstructured electronic health records, and real patient lives are on the line when critical details just get buried in all that noise. The stakes couldn't possibly be higher. But there was a massive catch to deploying AI to help with this, which we'll get to in a second. First, I want to introduce you to the hero of this story, the Mass General Brigham Air AI agent. This is not some theoretical model. It is a live deployed generative AI agent designed specifically to catch severe immune-related adverse events in cancer patients. And the research detailing its deployment gives us the ultimate roadmap for getting AI out of the lab and into the hospital.
To understand why AI has been so stuck, we kind of have to look at the old way of doing things. In traditional machine learning, researchers spent like 100% of their time tuning model weights on static, perfectly clean sandbox data. But think of that like building a multi-million-dollar Formula One engine and having absolutely no car to put it in. No tires, no pit crew. The engine is totally useless on its own. The breakthrough detailed in this research shifts the focus entirely away from just tweaking algorithms and instead looks at the real-world infrastructure needed to make dynamic, agentic workflows actually run on live electronic health record data.
Now, here's the number that should stop you. 80%. The researchers call it the 80-20 rule of clinical AI. Less than 20% of their total effort went into prompt engineering or building the model itself. Over 80% went into the unglamorous socio-technical work, data pipelines, security compliance, stakeholder alignment, ongoing monitoring. That 80% is the car, the tires, and the pit crew. To close that valley of death, the team identified 5 mandatory pillars for deploying agentic AI into a hospital's live infrastructure: data integration, model validation, economic value, drift management, and governance. Let's break down each one, starting with data. Picture a hospital on any given morning. Thousands of clinicians typing freehand notes, lab results pouring in, discharge summaries being written. It's chaos. Unifying all of that is like translating a dozen dialects into one clean language every single morning without losing a single detail that matters. Here's how they actually did it. Mass General Brigham pipes their epic electronic health record data into standardized OMOP and I2B2 mappings. An automated daily pipeline takes the messy free text notes, strips the formatting, and splits them into chunks that feed a shared embedding system. All of it moves over Azure private networks, so patient data never touches the public internet. Once the data's flowing, you hit validation. And here's where old-school ML thinking breaks down completely. A traditional model, once trained, mostly stays the same. A generative AI system doesn't. The underlying model gets updated by the vendor, sometimes monthly. Validating it is like inspecting a car that quietly swaps its own engine parts every few weeks. That means continuous testing, not a one-time sign-off. So the team ran aggressive red teaming and hallucination audits, deliberately trying to break the system with adversarial inputs. But just as important, dual annotator, human-in-the-loop review. Clinical experts manually checked the agent's outputs, catching things like the model inventing a symptom that was never actually in the chart, before anything reached a real physician. No hospital administrator greenlights a multi-million-dollar AI project without a clear return on investment. So the team tracked unit economics obsessively, separating fixed infrastructure costs from variable costs like API calls and compute. That work drove inference cost down to roughly $2 per 100 clinical notes processed. $2. That's what turns a flashy AI pitch into a budget line a hospital can actually approve. Even a validated, cost-effective model today can quietly go wrong tomorrow. Think of it like baking a cake, where the ingredients shift a little every day. Slightly denser flour, slightly less sweet sugar. The recipe hasn't changed, but the cake comes out wrong anyway. In a hospital, doctors adopt a new charting template, or a new drug hits the market, and the AI's baseline context shifts under it. That's data drift. The fix is always-on surveillance, automated tracking of embedding divergence and word frequency shifts, mathematically measuring how far new data has wandered from what the model was built on. Cross a threshold, and it triggers a review, without needing to retrain the whole model.
The fifth and final heavy lift is governance. This is the glue that binds the entire system together. In a hospital setting, you simply cannot rely on endless ad hoc email chains to figure out who is responsible if an AI makes a mistake. So the researchers utilized a strict RACI matrix. That's a project charter that explicitly defines exactly who is responsible, accountable, consulted, and informed for every single phase of the AI lifecycle. From deciding when to pin an API version to navigating really complex HIPAA compliance, everyone's role is hard-coded before the system ever goes live.
So what actually happens when you nail all 5 of these heavy lifts? Let's look at the real-world payoff. The Mass General Brigham team successfully deployed their IAE agent right into their live infrastructure. Its job? To hunt through messy clinical notes to detect severe immune-related adverse events in cancer patients receiving immunotherapy. These are toxicities that are incredibly difficult to spot manually, but they can be fatal if they're missed.
And the benchmark results? They are nothing short of spectacular. Remember, this isn't theoretical. This is live, real-world performance. The agent achieved a .91 macro F1 score, which is a massive indicator of both accuracy and recall. It hit a precision rate of .92. But perhaps the most mind-blowing stat of all is the human override rate. When clinical reviewers checked the AI's flagged events, they only had to override the system 2% of the time. 2%! This drastically outperforms older methodologies and proves that this system is actually genuinely trustworthy.
The crucial point here is how this translates to daily, on-the-ground operations. This entire pipeline, the secure extraction, the vector chunking, the agentic reasoning, and the final report generation, processes the hospital's targeted, complex medical notes in under 30 minutes. Every single morning, before the clinical research team even finishes their first cup of coffee, the AI has already scoured the records, caught dangerous toxicities, and routed them for review.
But here's why this explainer is so important. This research doesn't just boast about one single hospital's success. It provides the actual scalable blueprints for everyone else. They mapped out exact infrastructure tiers: foundational, sustainable, and scale. They outlined the exact compute required, the setup time, and the estimated costs to move from a single GPU sandbox pilot all the way up to a multi-region, real-time enterprise system. It proves that within the next 12 months, any hospital willing to tackle the 80-20 rule can use these specific tiers to deploy their very own AI copilots securely and efficiently.
We're entering an era where the bottleneck in medical AI is no longer the intelligence of the algorithm, it's the readiness of the socio-technical infrastructure. Mass General Brigham has shown us exactly how to build the car so we can finally unleash the engine, which leaves us with one massive forward-looking question. Will your hospital's infrastructure actually be ready to deploy the next breakthrough AI when it drops, or will it just stay stuck in the lab?
That's it for this one. See you in the next one.